Thank you, and thank organizers for inviting me here. And I learned a lot from these absolutely new topics and met a lot of nice people. So today I will talk about manipulation of the domain structure, and I will try to convince you that the magneto-elastic interactions can explain the formation and redistribution of the domain structure in antiferromagnets, and also can give a base for an analog of micr-a-magnetics for antiferromagnetic materials. And I will talk a little bit about the basics of magneto-elasticity, and then I will demonstrate how these ideas of magneto-elastic distressing energy can be applied for interpretation the recent experiments on the domain structure in antiferromagnets. So why this is so interesting and fascinating? Antiferromagnets are now considered as possible memory elements because they are fast, they produce no stray fields, and so on and so forth. But if we look at the real samples which we use in the experiments, we see that these samples are usually multi-domains, and it's unavoidable. The other thing, which is also very important, is the switching by the external fields and currents is related with the distributions of the domains rather than through the coherent switching, local coherent switching. So this you can see here, these recent experiments from the Nottingham group. The current is applied to the antiferromagnet, and the contrast shows, black and white shows the domains with perpendicular orientation of the antiferromagnetic vector, and after the current pulse, the domain region increases. And similar things we see in the nickel oxide, also by application of current. Moreover, the external stimulus can not only move the domain walls, but it can result in the total change of the domain structure. So before current pulse, we see nice and large domains, and then after the current pulse, we see shattered domains. The domain structure is fully changed. Moreover, these changes of the domain structure are reversible, as again can be seen from the experiments. If you see at the pictures at the same current values, you see the same domain structure, and this we also see in the electrical measurements with these materials. So this means that the domain structure is equilibrium somehow and should correspond to the minimum energy. And at this point, we come to the problem. Why? Of course, you can say that the domain structure in ferromagnets is well described as an equilibrium, as something equilibrium. And this can be made because in ferromagnets, we have an origin of the long-range demagnetizing fields. These fields appear due to the divergence of the magnetization inside the sample, and we can minimize. So when we describe the sample of a ferromagnet, we should take into account the demagnetizing energy, which is responsible for formation of the domain structure. However, if we look at the antiferromagnet, we see that in antiferromagnets, the order parameter, Néel vector, has no conjugated field like in ferromagnets, which can be responsible for the formation of the domain structure. And correspondingly, we have no magnetic charges, and we do not have any long-range fields of the magnetic origin. But this problem can be solved if we take into account magneto-elasticity. And I will show how the introduction of the order parameter related with the spontaneous strains in antiferromagnets can introduce long-range fields into the model. These fields originate from the stresses, and we can also introduce some charges, incompatibility charges, and describe the equilibrium domain structure. So what is magnetoelasticity means? We know this very well. So if the sample is ordered magnetically, then the lattice is deformed, for example, in the direction of the Néel vector. And this deformation is described with a so-called spontaneous strain, which is directly related with the orientation of the Néel vector. And the value of spontaneous strain is usually obtained from the condition that the stresses in the sample should vanish. They should be zero. But this very nice and naive picture does not work if we consider more complicated situations related with the real sample. The first problem appears when we consider an antiferromagnet grown on top of the substrate. Substrate is non-magnetic, and antiferromagnetic layer is antiferromagnetic. So below the Néel temperature, the antiferromagnetic layer is deformed while substrate is not. And this means that there is a kind of incompatibility between two layers. So to reduce this incompatibility, disruption of continuity of the sample, we need either add some material, or we need to relax somehow the stresses which appear at these points. The other problem appears when we consider inhomogeneous distribution of the domains in antiferromagnet. For example, if different regions of antiferromagnet are ordered with the differently oriented Néel vectors, then we again have this kind of incompatibility, inconsistency of deformations. So the conclusion from this observation is that the spontaneous strain itself is not enough to describe what happens in real antiferromagnetic samples below the transition temperature. And this brings us to the description which should be based on the mutual or self-consistent considerations of the magnetic degrees of freedom and elastic degrees of freedom. And what we can learn from these equations is that in principle, the equation for elasticity are equation for the divergence of stresses. Yeah, you see here we have the gradients, and the gradients of the antiferromagnetic vector can be the sources of additional stresses and strains in antiferromagnetic material. So how can we describe the real structure in antiferromagnets, and how we can find these real strains which can occur in the materials? So the idea was first suggested by Kleman and Miltad in 1962 for ferromagnetic materials, and the idea was based on consideration of the plasticity of the elastic bodies. So what we can do, we can consider the strain split it in two parts. One is spontaneous strain, which maps exactly distribution of the antiferromagnetic Néel order parameter. But then we need also to take into account the plastic part, which appears due to the relaxation of these stresses related with incompatibility. And this idea is really great, and the elasticity theory has a technique which allows to find to calculate these plastic strains. And this is shown in this table. So there is approach in elasticity, which is called incompatibility approach, in which instead of working with the displacement, we can try to find the deformations as a function of coordinate. But for deformation, we have the following type of equation, where in the right-hand side there is a tensor of incompatibility. This is well mathematically defined object. And I would like to stress that these gradients, they both are applied to the deformation field, and the position of gradient means only the coupling with the corresponding index of the strained tensor. And this approach is very convenient for antiferromagnets because the deformation is a value which you can observe directly. So, in application to antiferromagnets, we can introduce this incompatibility in the following way. So, we assume some distribution of antiferromagnetic vectors inside our sample. Then we calculate spontaneous strains, exactly like local homogeneous deformations. And then we calculate this incompatibility using the following recipe. And what is nice with this approach is that it also allows us to make connections to the magnetostatics in ferromagnets. Why? This equation has the green functions which have exactly the same asymptotics as the Coulomb green functions, and which we use in magnetostatics. So this incompatibility can be considered as analogous of the magnetostatic charges for demagnetizing effects, and then we can consider spontaneous strains as a primary order parameter which creates, whose incompatibility is the source of these additional distressing fields. So basing on these ideas, we can calculate the additional strains which appear due to incompatibility of the primary spontaneous strains, and also introduce distressing energy, which now couples Néel vectors in different points, but it's not linear, it's bilinear in the Néel vectors. And the kernel here is also very similar to the kernel, the corresponding kernel in the magnetostatics. So it's simply depends on the space as dipole fields. And of course, these expressions are quite complicated because this K tensor is a fourth order tensor, it's related with the gradients, but in principle, everything is calculable, and these functions are well documented. So this can give us a basis for so-called Micr-a-magnetics, so micro-magnetics for antiferromagnetic materials, but unfortunately it works only for statics. So I don't know how to apply it to dynamics at this moment. So now I want to illustrate you how this technique works. Some very simple examples. And first we consider the distressing effects which comes from the substrate. So the idea is very simple and very similar to what we have in ferromagnetic materials. So if we try to calculate the leading term of this distressing energy, which originates from the incompatibility between the substrate and antiferromagnetic layer, then we found out that this energy is first proportional to the sample volume and is quite large, and then it can be expressed through the averaged values of Nn. And this tensor is equivalent to the demagnetizing tensor which we use in ferromagnetic materials. So what would happen if we minimize the energy of the whole sample with account of this distressing energy. The calculations shows that the equilibrium state of the blanket film, which is infinite within the plane, but the film placed on the substrate, the equilibrium state corresponds to the such distribution of the antiferromagnetic domains. And the contrast shows the difference between x squared and y squared component of the Néel vector. These domains have the same period in both x and y directions, and this Micr-a-magnetic approach also allows to estimate the period of this domain structure as a function of the thickness of antiferromagnetic layer. So we can get analog of Kittel formula for the antiferromagnetic case. The other, and now look at what we see in the experiments. Experiments show we indeed have a kind of these domains, square type domains. Of course, it's not so nice periodic structure, but nevertheless, we can see a kind of periodicity which is associated of these white and black domains.
Why are these squares?
Here, why are these squares?
Yeah.
Can you specify your question?
Why not triangles?
Why not triangles? Because we have only two types of the domains. I will be back to your question in 2 minutes. You will understand it. So, to answer your question, we need to consider another problem. The problem of the domain boundary. So, the distressing, or this incompatibility, appears also when you try to match two slightly deformed domains. And this means that the energy of the domain wall in an antiferromagnet with account of the magneto-elasticity is strongly dependent on the orientation of the domain wall. In principle, it's very difficult to calculate the full energy of the domain wall because it diverges, so it scales proportional to the sample volume. But we can calculate the energy per unit volume. And then what we can get, first I explain this from hand-waving arguments. So if we have two antiferromagnetic domains, then it's obvious that in some directions we can have incompatibility because the length of the lattice in this direction does not match the length of the lattice in the same direction in different domains. Imagine that this is a domain boundary, and here you have magenta domain, and here you have blue domain. So you need to put some extra material in order to fit them. But this effect strongly depends on the orientation of the domain wall. So the incompatibility is angular dependent, and there are some directions in which it's exactly zero. You see, in these directions, two lattices perfectly match. The distances perfectly match. And this can be calculated using this distressing energy. So again, if we look at the energy of the magnetic domain wall in an antiferromagnet, it's isotropic, no angular dependence. However, if we take into account magneto-elasticity, then we get this cosine square dependence, which shows that there are only certain directions of the domain wall which have minima energy. And for these orthogonal domains, domains with orthogonal Néel vectors, these domain walls go exactly along the hard axis, hard magnetic axis, and therefore we have these squares. So they are orthogonal. If you consider, for example, nickel oxide, which has 120-degree domains, then the domain walls will match the triangular symmetry.
Maybe I can specify. So you start with a square-shaped sample, and then you get squares. If I start with a triangular-shaped sample, do I still get in the center squares and some stuff at the edges?
I will answer your question in 2 minutes.
Can I phrase your expression in a different way? So I don't care about the shape of this. Why do I not get lamella? Stripes, because that's what you get for ferroelastics. And in a sense, this is
1 minute more. So my next slides. Okay. So now I show you the experiment for the blanket film. What we are, when we say blanket film, we mean that the size of the film is so large that I can forget about the edges of the sample. I take into account only the substrate and the antiferromagnetic layer. And what we see here, so we see that the domain wall orientation is exactly along the hard axis. So this, as predicted with the theory. But then back to your questions. You say, why not to make a stripe? Yeah? Okay, I have something for you. Let's make a stripe. Then what can happen? Of course, these long-range fields are very important if you have a boundary. And the effects would be pronounced if you have rather thin stripe to see these boundary effects. So in our modeling, we consider the boundary conditions in the elastic theory are extremely complicated. So we considered the most easy case when the boundary conditions are given by the magnetic effects. So I assume that the boundary of the sample has additional anisotropy, which favors orientation of the Néel vector along the cut. Yeah? But still, once we have this boundary condition for the Néel vector, we have these long-range forces which imposes some additional conditions inside the stripe. And then what happens? First of all, it's obvious that if I forget about the substrate, then the sample would be happy to be oriented along this easy direction, which is now a little bit biased compared to the bulk. But if I have a substrate underneath, then still I have distressing energy. So the system wants to split into the domains. So let's look what would be the optimal shape of the domain in this case if we have stripes. So for this, we need to calculate this energy. And what I did, I calculated it as a function of the position of the cut. So what is shown here, it's this square, let's say. Okay, it's not square, but it's, yeah. So it's the one domain, and this other domain in the blanket film. And then I tried to look at the position of the cut and calculate the energy. And it's obvious that in this region and in this region, system is happy because the domains are parallel to the anisotropy induced by the surface. But in this part, the system is unhappy, and then it gives to the increase of the energy. So if I move this imaginary position of the cut, then I see that the minimal energy would be if the domain walls meet exactly at the surface. In this case, I minimize the area of the unfavorable domain which touches the surface and minimize energy. But then there is another effect. So let's look at the angular dependence of the surface energy. Now, what I do, I start from the 45 oriented domain walls, which correspond to the minimal energy in the bulk material, and then look at the surface effect. And again, this area contributes to the increase of the surface energy. So what happens if I change the angle between the domain walls? The energy will diminish until and it takes its minimal value when the domain wall closes. So the real shape of the domain in this case should be the result of the competition between this surface domain, domain wall energy, distressing energy, and of course magnetic energy. And what we see in the experiments fits very well again to this model. So these are stripes of the same material as I showed you. And then these are stripes of the same length but different thickness. And what we see that the domains, first of all, we see that the edge or this surface imposes some additional anisotropy. So if we cut in this direction, then the sample is almost black because it favors this orientation of the Néel vector. If we cut it in the 90-degree rotated direction, then the sample is almost white. This means that the other direction of the Néel vector is preferable. But then the domains of the opposite side, they have a shape of the lenses or rhombuses. And these lenses, they started exactly at the edge of the sample for all samples which we looked at, you see. And then they, instead of making 45 degrees with the sample surface, as I should expect in the bulk materials, these lenses are almost closed. So the system tries to diminish this width of the domain, and these lenses shapes are quite reproducible. And that what is also interesting, we tried to look at the different thicknesses and try to find whether the parameters of these lenses related with the shape effects, with the dimensions of the sample. And surprisingly, we find out that the proportions of these lenses and their real sizes are some internal parameters of the material. So they do not change when we increase the thickness of material. You can think that this is a little bit longer lenses, but if you look attentively, it's two lenses which meet together at some point. So with this, I came to the conclusions. So I thought that somehow we made a bridge between antiferromagnetism and elasticity, and and this allows us to describe the domain structure observed in the experiments, and we also hope that it can help us to explain transport measurements and maybe dynamics. And here I show my collaborators. So the experimental part was done mainly by Nottingham group, and Jairo, who pays and who is my favorite boss. And this.